Welcome to Maths with Bob. Today we're looking at matrices and we're looking at eigenvalues and eigenvectors in particular. And these obviously occur for square matrices. Okay, here we have a square matrix, and the vector, is in fact called the eigenvector. Okay, is a column matrix, and it is an eigenvector if we can actually say something like this, that in fact I get the matrix multiplied by that vector, and it is equal to some constant, a scalar, times the vector itself. Okay, so for each eigenvalue, there is an associated eigenvector. Okay, so each eigenvalue has an eigenvector. And obviously, it depends on the matrix, okay, for the actual eigenvalues. Okay, so if you like, obviously there's an eigenvector for each eigenvalue. Okay, the set of eigenvalues is called the spectrum of the matrix A. Okay, the largest of the, in absolute value terms, of the eigenvalues is called the spectral radius of the matrix A. And some people actually think of this as like basically applying some sort of deformation to a vector, and it actually preserves its direction. Okay, now what do we mean by that? Okay, I'm just going to have a look at Geogebra, and we'll actually have a look. But basically, yeah, okay, let's have a quick look here. This is our matrix A, okay. Okay, so our matrix A is this one here, 6, 2, minus 5, 1, 1, 1 in the second row, and obviously you can see here 8, minus 2, 7. Okay, so our eigenvector is minus 1, 1, and 2, and our eigenvalue is 2. And we'll see in a minute that we're going to go through an example and show you how we get all this. But basically, if I get this A, this matrix A, and I multiply by this, you can see here, eigenvector 1, minus 1, 1, 2, is actually equal to 2 lots of this, the actual eigenvector minus 1, 1, and 2. Okay, so we're actually, if you like, the matrix is going to be applied to the vector, and the vector is actually just going to be a multiple of the original vector. So it's, if you like, its direction is preserved. Okay, so let's actually have a look at Geogebra. Okay, I've basically created well, I haven't created the matrix yet, but let's create the matrix. Okay, this is create a matrix, and we'll call it, let's actually have a look. Where's that matrix? Can't see it at the moment, but let's rename it matrix, say A. I think this is what we called it before. Okay, all right, so if I now go, I've actually created a, you can see here the matrix, the vector minus 1, 1, and 2 already. It's called U. So if I go vector, then I just go multiply A times U. Oops, that's lowercase u. Okay, and press enter. It's already done it for us actually. You can see here, let's actually just change the color of the vector. Okay, let's color, just change it to red or something and make it maybe a little bit thicker. Okay, so we can see it a bit better. Okay, so you can see here the matrix has in fact extended, or by a factor of 2, basically. The 2 is the eigenvalue. Okay, this is the vector, and you can see here this matrix A, the actual deformation, has basically preserved the direction of U, and actually the preservation, or the weighting factor, is 2. That's called the eigenvalue for that particular vector. Now, just to show you, I've just generated like a random matrix here to show you. If we create another matrix, let's actually create another matrix and recall it, rename it, say G or something. Okay, and if I go here, vector, and I just basically go G times U now. Okay, just make, oops, what happened there? Okay, all right, so now where's W? Okay, W is over here. Okay, I'll just show you object properties. We'll make it a bit thicker and change the color so we can actually see it a bit. It's a bit hard to see, purple. Well, okay, well, it's a bit hard to see actually. There it is there. Okay, but you can see here that that matrix G obviously didn't preserve the vector, the original vector U's direction. Okay. Okay. So if you like, well, we'd have to actually find what vectors that other matrix G would actually preserve. So this would have to go through and find the eigenvalues and eigenvectors actually for that particular matrix. So it's different for each different matrix. So it's like a different deformation, if you like. And you can see here that that the original one, U, okay, here, let's just take out this one. This one, actually, if I put in V now, okay, you can see here it's just doubled its distance, or it's actually length, if you like. And all right, okay. Well, okay, how do we actually work out the eigenvalues for a matrix? Okay, well, basically, well, if we write the equation, oops, let's just use a highlighter. This equation, hopefully that'll disappear shortly. Yes, it's disappearing now. Okay, so here is our equation. And we can't solve it as it stands, basically because this is a scalar. Okay, we need to create a matrix equation. So we need to multiply it by I, a unit matrix of the same size as basically A. And then we need to solve this one here. Okay, now what we need to do is you move everything to the left. Okay, take out a factor. Okay, now you can see here this is actually a homogeneous equation. Okay, all zeros down here. Okay, and basically what happens is you have to find the determinant of this. If that's equal to 0, okay, then a non-trivial solution will exist to this particular equation. Okay, so we need to introduce lambda, and you can see here I've done it down here, and this is what we now need to. We need to find the determinant of this expression here. Okay, okay, so this is matrix A minus lambda, the scalar, which we don't know yet. Okay, I being the unit matrix 3 by 3, 1, 1, 1. You can see here, actually, we've just multiplied it here by lambda, and this is the original matrix A. Okay, which we're going to be looking at in detail. Okay, all right. So we now have to, if you like, work out the determinant of this expression here. Okay, so let's have a quick look. Okay. Well, first we need to expand the determinant, okay, and you might remember the determinants go plus, minus, plus, okay, and then we have to basically multiply all this out. We'll get a polynomial. This is called the characteristic polynomial. Sometimes that determinant is called characteristic determinant, but we end up getting, if you like, here this is the polynomial we get here, okay. We will multiply it by -1 because it's equal to 0, and we'll end up getting a polynomial equation here, which we need to factor. Okay, this is a cubic, so you can just try some of the, well, I always look at the +2 and try some of the factors of +2. Okay, and luckily, if you like, 1 works, therefore lambda minus 1 is in fact a factor. Okay, so what is the resulting polynomial after you divide it by lambda minus 1? Well, I'm going to go through in a second the polynomial long division of how we actually do this. Well, okay, here we have the polynomial long division. So how do we do this? Well, I'll just go over quickly. You might remember, okay, it's this term. This is a leading term into the leading term. So it's basically lambda into lambda cubed goes lambda squared times. Then we multiply lambda squared by lambda and also by -1, and then we write it under here. So let's actually do that. Let's put that underneath there. Okay, so we need to, here we go. Oh, no, not that one. Here we are. Yes, here we are. Okay, so we have, if you like, lambda squared times lambda is lambda cubed, lambda squared times -1 is minus lambda squared. Okay, then we have to basically subtract, so we need to use one of these negative signs here. Okay, now we can bring this term in. Okay, so now we need to subtract. Okay, well, obviously lambda cubed minus lambda cubed is 0, minus 2 lambda squared minus lambda squared is, okay, plus lambda squared, so it's actually minus lambda squared. We bring these terms down. Now, okay, it's going to be leading term into leading term again. Okay, so it becomes lambda into minus lambda squared, which goes minus lambda times. Okay, there we go. Minus lambda times lambda is minus lambda squared, and minus lambda times minus 1 is plus lambda. So here we are. All right, okay, we're getting the terms organized now. Okay, and then we're going to subtract again. Okay, so let's subtract again. Okay, right. And hopefully, let's have a quick look. Does this work? Okay. Okay, lambda squared, minus lambda squared, minus lambda squared. Okay, 0. We end up getting minus 2 lambda and bring down the 2. Right, now we go lambda into minus 2 lambda, goes minus 2 times. Okay, and then minus 2 times lambda. Okay, and minus 2 times minus 1. Okay, here we are. Basically, and as you can see, obviously when you subtract those, you'll end up getting 0. Okay, so what does this mean? Well, it just basically means that we're going to have to factor, obviously, lambda squared minus lambda minus 2, which is not too bad to factor. Okay, we end up getting this, and if it's equal to 0, you can see here, basically we're going to get 3 eigenvalues. Okay, let's try and put this down the bottom here. Okay, all right. Okay, so they're going to be, if you like, 3 eigenvalues, 1, 2, and minus 1 for that particular matrix A. Okay. All right. Now, okay, so we've got these eigenvalues, 1, 2, and minus 1. Okay, and we need to put them into the basically back into the equation here. You can see here. It's basically, I guess the easiest way to say it is substitute them in turn into this particular equation. Okay, basically, and we end up getting that first up, we put them in the lambda equals 1 into 6 minus 1, okay, it's minus 7. Then we basically augment it with the zeros, okay, zeros, because the zeros on this side, we need to try and solve it basically for this particular vector here, x. Okay, so these are the augmented matrices which we're going to use Gaussian reduction on, and you put 2 in. Okay, 6 minus 2, minus 8, etc. Okay, minus 1, so it's 6 minus 1. Okay, 6 plus 1, or minus 6 plus 1, minus 5. So these are the augmented matrices which we're going to have to actually basically solve in turn. Okay, all right, so for lambda equals 1, we have to do a bit of work. You can see here, basically, it's just basically, I just go over, basically this is what happens. Row 1 becomes equal to row 1 plus row 3. So if you add the bottom row to the top row, you end up getting, okay, we get a couple of very similar sorts of rows here. And we can make one of these rows 0 quite easily. Okay. Basically, if we just take off row 2 minus row 1 and make a whole row of zeros, okay, this indicates obviously it's a redundant system, and we just let, you can see here that z equal a, and then from the other rows, so from row 3 down here, we would have to actually just put in minus 2y minus 2z, which is now a, obviously, and then work out what y is, and then back substitute into the top row to get what x is, and eventually we end up getting, okay, we end up getting this expression here. Okay, let's see if I can put a circle around this. Okay, not too bad. Okay, so this is this is our eigenvector for any value of a. So we normally would put in an easy value. So if you put in, say, a is minus 1, you end up getting that this is the now eigenvector associated with that lambda equals 1, which is the eigenvalue. So this is the eigenvalue lambda equals 1 eigenvector. Okay, right. Okay, all right. So obviously, you can see here, what does that mean? Well, it just means now that if I apply that deformation to that particular vector, it actually preserves its length and remains the same. So let's actually have a look at that in Geogebra. Well, okay, here we have Geogebra. I'll put in a new vector. You can see it down here. It's actually pointing down that way. Okay, now let's actually have a look at when I apply this matrix to that particular vector. Okay, so you just type in here vector. Okay, and we just go A times U now. Oops. Okay. Okay. Now, it looks like nothing's really happened, doesn't it, really? Okay, but let's actually change the color of this just to show you. Okay. Let's change it to, say, okay, blue, make it a bit thicker. Okay. All right, I don't know whether you can see now that, but basically it has actually preserved its direction, obviously. That's the idea of the eigenvalues and eigenvectors. And it's actually a multiple. It's the scalar, the eigenvector is multiplied by 1. I don't know whether you can actually see it in the algebra window here. But if we take that vector out, it's just exactly the same vector. It's 1 times it itself, basically. But anyway, this is just to show you that, in fact, this particular eigenvalue of 1 has actually multiplied by the vector. So it's actually preserved the direction exactly, if you like. Okay, well, let's continue on. We're now going to basically use, if you like, the next eigenvalue, lambda equals -1. And we put it in, and we have to do some row reductions, obviously. And you can see here, we go through a process, swap a couple of rows, and we do a bit of work on the different rows, try and reduce them. Now, from here, we could actually reduce one of these rows to 0 quite easily. But I just think that, if 12y is 0 and minus 18y is 0, obviously y is 0. So if y is 0, then you let, say, z equal a, for instance. It doesn't matter. And then back substitute into the top row and to try and work out what x is. So if we get y is 0, z is some a, and x is minus a. So we end up getting the vector over here. Okay, so this is now our general vector, if you like. Okay, the general vector you can see here is not terribly well, but basically minus a 0, y was 0, and z was a, actually. Okay, and you normally would put a particular value in. Okay, so 1, nice easy value, and you end up getting this vector for that particular eigenvalue. So the eigenvalue of -1 gave us this vector here, x2, -1, 0, and 1. Okay, and obviously you can see here, what does that mean? Well, it just means, okay, I'll just try and we'll do this in Geogebra too, just to show you, but what's happened is that particular vector has actually, its direction has been preserved as well. Okay, so that particular deformation applied to this particular vector has actually, well, preserved, no, I should say direction. It's actually basically changed its direction. Well, okay, it's a scalar multiple of the vector. Okay, and remember, lambda can be positive or negative. This actually, -1, will change the direction, and we'll have a quick look at that now also in Geogebra. Well, here we are again with Geogebra, and you can see here the vector u is actually, I've put in the new vector, -1, 0, and 1. Okay, now we're now going to just multiply the deformation, or the matrix A, by this. So we just go vector, okay, and just type A times u again. Okay, now let's actually change the color of this too. But you can see here on the Geogebra, it's actually just put it in the opposite direction for us already. Okay, let's just change it to, say, purple. Okay, all right. So basically, you can see here that the deformation has actually changed the direction of that vector. Okay, by a factor of -1 actually. So it's just changed. Its length is obviously the same, but it's just in the opposite direction. So that's what the negative eigenvalues do to the vectors. They just change their directions. Okay, and you can just see here, it's just a matter of applying that, if you like, that vector, well, the matrix and the vector multiplication. Okay, let's pause. Well, here we are back again, our final eigenvalue 2. Okay, so we put that into the matrix. Do some row reduction, obviously, as you can see here. Nice to swap that one up the top there. Okay, we do a bit more row reductions here, and you can see here we end up having, we can make row 0 quite easily just by adding this row to this row. Okay, I didn't put that in, but it's quite easy to do. Like obviously minus 6 plus 6 is 0, and 3 plus minus 3 is 0, so we get a row of zeros on the third row. Okay, then we let z equal a, and then we actually go back and do the substitutions. We end up getting, okay, what do we get? Well, z is a, we get y is a on 2, and x is minus a on 2. Okay, so we end up getting, this is now, okay, our eigen, if you like, eigenvector for that particular eigenvalue. Here we are. Here it is. Minus a on 2, and a. Okay. We would obviously that's for any a. And if you want to put a particular value of, let's actually move that across. Here we go. Sorry, wrong way. Okay, let's move it across. So basically, if a is 2, that eigenvector becomes what? Minus 1. 1 and 2. Okay, this is the eigenvector. This is called x3. This is the third eigenvector. Okay, basically, and this is the eigenvector for lambda, which is the eigenvalue of 2, which is what we started off with actually. And you can see here what this means is obviously a times that particular vector is double that particular vector, and we'll have a quick look at that again in Geogebra just to show you that obviously this is just preserve the direction again. Well, okay, here we are again with our third eigenvalue and vector. Well, it's the eigenvector you can see here, u minus 1, 1, and 2. Let's actually just type in vector. Okay, we're just going to go a times u. Actually, there we are. And again, you can just see it's doubled its length here. You can see it's doubled its length. And if you like, just change the color to some other color for a bit of a change. Okay, and change its, make it a bit thicker. Okay, all right, okay, so here it is. Okay, you can see here that it's actually it's doubled its length, so the direction obviously is preserved. Okay, and okay, so what are we going to do with all these eigenvalues and eigenvectors? And that's what we're going to be looking at next. Well, okay, what are we going to do with all these eigenvalues and eigenvectors? Well, they actually can form different matrices, and they help us what's called diagonalize a particular matrix A. Now, if we want to diagonalize matrix A, well, you might think to yourself, why would you want to diagonalize a matrix? Well, basically, it's much easier to handle if you have a diagonal matrix, especially if you're going to compute powers of a matrix, actually. Okay. There's lots of uses of these sorts of ideas in speech recognition and facial recognition software and stuff like this. So this is a very useful idea of, when you find the eigenvalues and eigenvectors, put them into matrices and compute what's called the diagonal, well, the actual eigenvectors form this matrix C here. You can have a quick look here. These are the eigenvectors down here. Okay. The eigenvalues actually come down this way, and indeed this is the actual diagonalized, if you like, matrix A. This is the diagonalized matrix, but the trouble is you need to do a multiplication to actually to diagonalize A. So here's A. You need the, if you like, the C here, which is the matrix of the eigenvectors, but you will also need to compute the actual inverse, or if you like, C to negative 1, or we need, if you like, to invert matrix C. Now let's actually have a look at that in Geogebra. Well, here we have the spreadsheet version. Let's create some matrices. I think let's call this one, I think we call this one C. Okay, we call this one was called A. Okay, we now need to also invert C, so we need to actually to go So we need to invert the matrix. Invert matrix. Here we are. Invert matrix. Now, what matrix do we want to invert? Well, invert matrix C. Okay, here's matrix C. This is actually inverse of C, so let's rename it. Inverted C. Okay, all right, so we need to do the multiplication. So we have to go inverted C. Inverted C. We need to multiply that by A, and then multiply that by C. Okay, fantastic. Here we have it. Rename it. Okay, so this is D, the diagonalized matrix. Okay, so this is the one which you can see here has the eigenvalues down the diagonal. Okay, all right, well, this is a fairly long video, and thank you for watching and persevering. Bye for now.